So from here on out, our tests will not be on Aware. They will be on AP Classroom. So they will be College Board questions, so they'll be very similar to the questions that you'll see on the actual AP exam. They will be modeled after the AP exam, meaning approximately half of the points will come from multiple choice questions, approximately half the points come from free response questions. Once we do a few College Board style free response physics questions, you'll get used to how the scoring guidelines are designed to grade those questions. Those questions, the FRQs on the actual AP exam, there's going to be 5 of them. They're either worth 7 or 13 points. For the actual answer to each of those questions, FRQs, the actual answer is at most worth one point. So if you have a multi-part, say a 4-part question that's worth 13 points total, the maximum number of points for the answers will be 4. And sometimes the scoring guidelines don't even award points for correct answers. What they award points for are things like the student recognizes that Newton's second law is at play, right? And then they give the reader examples. How can they tell you that? Well, they can explain it in words, or they can write the equation. If they don't explain it in words and they don't write the equation, or they just start writing equations but with numbers instead of symbols, guess what? You don't get those points, okay? This is where the students that don't like showing work and that fight me on it, where they start falling behind and not doing as well, even if they're getting the right answers. I'm sorry, this is an AP exam. Yes, I'm here to teach you physics, but I'm also here to get you ready for the AP exam. So you're going to have to solve FRQs. And when when I grade your test FRQs, I need to see your thought process. If I can't follow your thought process with what you've given me, then you lose massive points. Okay. Well, the easiest way to get the maximum number of points is to do what I'm asking you to do, because, I know what they're looking for when they grade this stuff. Okay. So you learned a little bit about free body diagrams. You learned a little bit about net forces, and they either can cause accelerations or they can prevent accelerations. So what I'm going to do is extend. We're going to talk about a lot of those concepts, and we're going to analyze this situation here. So I got this set up here. I got a scale so I can measure masses. So what I'm going to do is I'm going to be able to measure the mass of this cart, and I can put more masses on top of it, right, to make it more massive. And I can measure that mass with my scale here. I can measure the angle of elevation of my ramp with my little angle indicator, right? Little protractor guy there. And the question is going to be, how much mass do I need to load up onto the hanger here in order for the system to be at rest when I let go? The system will not be at rest here. When I let go, he wants to accelerate down the ramp. This is what you expect, right? You got barely any weight here. But you might think, well, if I put enough weight here, well, then it should accelerate in the other direction. And sure enough, if I put the big mass here, the 500 grams, it does accelerate that way, okay? So I want to calculate how much mass I need to put here so that when I let go, nothing moves, okay? And the system will not accelerate. It will be at rest, okay? Now I could, of course, just load up masses more and more and more until I find that point. But that's not physics, right? That's just trial and error. We want to calculate it and then load those masses on to see if it actually works, okay? So in solving this problem, we're going to talk about a whole lot of different physics. And it's going to tie together essentially everything you watched in the videos from Flipping Physics. Excuse me. Before we do that, I do want to talk a little bit more, sorry, I'm recording this, you need to remember that, about tension forces, okay? I do need a volunteer. I have been washing my hands. I'm very nice and disinfected, but I'm not even touching the thing that I need you to grab onto. So can you grab that block of wood for me, please, Brenna? And then come, stand next to the file cabinet there. And come this way, just right there. Back up maybe just a little bit. And so here, I got 2 blocks of wood. Now Brenna and I are going to put some tension on the block. Okay, just pull it a little bit. Now, If I lessen up on the tension, what way is my hand going to move? Exactly, towards Brenna, right? When we put tension in the string, it's pulling my hand towards Brenna. What if Brenna lets go, or lets up on hers? What's going to happen? Oh, it's going to go towards me, right? Yeah. So not only when we put tension on the string pulls me that way, it pulls Brenna this way. Okay? Yeah, that's good. Thank you very much. I don't want to touch it. Thank you, Brent. So what that means is anytime a string has tension in it, it's exerting a tension force on both things that it's connected to. Okay? If it's looped over a pulley, it's actually pulling on the pulley. Okay? The tension here, when I pull it down, is what's causing the pulley to rotate. It's the tension force acting on the pulley. Okay? And it's always the tension force acting on the cart there is pulling up the ramp. The tension force acting on the pulley is pulling down. The tension force acting on this mass is pulling up, right? So wherever the string is connected or is looped over, the tension is going to be the same on both of those objects. Okay. What explains that? Newton's third law. We'll talk about that in more detail in the coming days. But for now, just understand that the tension's the same. Okay. All right. And so this is the situation. The situation is you're going to tell me, I'm not even going to know after we do our analysis, you're going to tell me how many additional masses to load on this guy. You're going to tell me if you want to change the angle of the ramp or not. And then we're going to calculate how much mass we need to hang on this guy in order to essentially create a state of equilibrium, stable or static equilibrium where nothing's going to be moving. All right. Whenever we solve problems like this involving forces, it definitely helps, especially when we have a system of two objects. Here I have two objects that are going to be moving, right, simultaneously. So I'm going to say the system is the two objects. I have a system of two objects that I need to analyze with regard to the forces that are acting on those objects, okay? It definitely helps me, especially, me for sure, to draw a little diagram, right? So it's not going to look exactly like the setup, but essentially I have a mass here that's connected to a string that is looped over a pulley that then a hanging mass is attached to. I'm going to label some things on my diagram here. I'm going to call this guy M1 and call this guy M2. And I'll say that my angle of elevation for the ramp is angle theta. And given some theta that we can measure, given some mass M2, I want to calculate a value for M1 such that the system is in static. I'm maybe 50% today, guys, so don't judge me if I mess up. Isaac, don't judge me, Isaac. I know you're judging me. Static. What does static mean? In the context of static equilibrium.
Like,
not changing. The opposite of dynamic, right?
Very true.
So static, you can be in dynamic equilibrium too, but static equilibrium means everything's sitting still and it's not moving. Right? Another way of saying static equilibrium or any kind of equilibrium is saying that the net force on the system is just zero. Right? We learned that from Mr. Flipping Physics. If we're in equilibrium, the net force is zero. You knew this from middle school. An object or a system of objects will move in a straight line at constant speed unless acted on by an external net force. An object in motion stays in motion, an object at rest stays at rest. Right? All right. Okay. Now, before we analyze this situation, I'm going to throw out another term. Static equilibrium, not moving, continuing to not move. I'm also going to throw out another word, another term, I should say. Ideal pulley. We are dealing with a pulley in this situation. At this point, we don't know how to deal with real pulleys. Okay, we can only deal with ideal pulleys. We won't be able to deal with real pulleys until we learn about torque and rotational equilibrium, which is second semester. Now, when I say ideal pulley, key word there is ideal. Where have we seen the word ideal in our study of science before this year? Gas. Ideal gases. Now, you find your friends in second period, and you get mad at them, because no one could tell me anything about ideal gases in my second period AP Physics 1 class. You learn gas laws in general in regular chemistry.
Well, I don't know. I don't think Nolan took chemistry. Wait, Ethan definitely took chemistry.
Yeah, yeah. You can't tell me that even in on-level you didn't learn this equation.
Imagine not know this equation.
Yeah, Dan.
We're actually going to use this equation as a jumping off point to describe how we can experimentally determine Newton's second law of motion. We're going to do that. That's going to be our next lab. Okay. The reason why I brought this up, what is this law called? The ideal gas law. And it is from this law that all other gas laws come from. Charles' law, Boyle's law, Avogadro's law. All those laws, they come from the avocado law. They all come from the ideal gas law. By the way, it's about to start getting colder. When it significantly gets colder, what do you have to do with your car tires?
Pump it up.
That most people don't do. You got to pump it up. Okay. Why is that? Well, because what does N stand for in the ideal gas law? Number of moles. Does the number of moles of gas change in your tire when the outside temperature doesn't change? Or when the outside temperature changes? No. So that's a constant, right? If N changes, you got a leak in your tire. And you're losing N. You're never going to gain N unless you have a pump hooked up where the pressure in the pump is bigger than the pressure in the tire. But atmospheric pressure will never be bigger. What did you say about R? What's R?
Gas constant.
It's the ideal gas constant. Okay, so that's by definition constant. The volume of your car tires doesn't change too much. Yes, when it starts to get flat, it gets a little smaller, but not much smaller. Okay, it's essentially the same volume. So as the temperature goes down outside, what happens to the pressure in your tires? It also goes down. Right? Notice to analyze that relationship between pressure and temperature, we have to assume that everything else is constant. That's where the gas laws come from, right? You assume everything else is constant, then P1V1 equals P2V2, if everything else is constant. Not only that, if I divide both sides by NT, I get the ideal gas constant, right? This is a very interesting result, or just a very interesting way of looking at an equation you already knew. Take any gas. If you know the volume that gas is contained in, you know its pressure, you know how many moles of gas there is, and you know the temperature, you divide the product of the pressure and volume by the product of the number of moles and temperature, you get the same number, no matter what gas you're dealing with, as long as it's behaving ideally. Okay? So we're actually going to look at the equation, this type of an equation in a little more detail when we start experimentally determining Newton's second law on our own. But for now, I want to focus on that word ideal. So how many gases in the universe do you think behave ideally with 100%? Pretty much none. Okay. There are extreme cases where you got physics that's way beyond my comprehension, like of the very small, if you're talking like quark, gluon, plasma. I'm not making any claims about that stuff. I am making the claim that for any gases that we typically experience in our everyday lives, they all behave ideally by about 99.99999%, right? But they're not 100% ideal because there's some assumptions that go into an ideal gas. Does anyone remember what those are? There's like 4 or 5 assumptions. And these are incorrect assumptions. One of the things, we assume that there's 0 particle size. Right? The ideal gas law is only valid if gas molecule size is 0. Is that true? No. But the sizes of gas molecules in this room as compared to the average distances between the gas molecules, is so small that we can assume that it is zero, and it's fine. We don't lose that much accuracy in our predictions. Because, again, it's close enough to zero that we could just assume that the zero size. We also assume that when the gas molecules collide with each other or with the walls of their container, that they lose no energy. Those types of collisions, something we study in this class, are called elastic collisions. They're bouncy collisions. They lose no energy. Does that actually happen? No. When gas molecules hit each other, they lose a little bit of kinetic energy in the process and generate a little bit of heat energy. But for most gases, that effect is minimal. You can have a gas in a balloon, and if you have it contained in nice, strict conditions, that gas will behave ideally, according to the ideal gas law, for 100 years. And you won't make any measurements that would tell you that it's not behaving ideally. But in reality, you give it enough time, it's not going to behave ideally all that time. But for the most part, we can assume that all gases we deal with in everyday life behave like ideal gases. So even though those assumptions are not true, we can still use the ideal gas law and have very good results. Okay. Why am I pointing that out? When we talk about ideal things like this, we mean those ideal situations where we assume things that aren't true, but they're close enough to being true that we can kind of neglect their effects. So when I talk about an ideal pulley, if an ideal pulley actually existed, it would be massless, because just like objects with mass have inertia and they resist a change in motion, a pulley with mass is going to resist a change in not just motion, but a change in rotational motion, okay? Which means we do have to have some kind of torque to get something to start spinning if it wasn't spinning before. But if we have a pulley that has a small enough mass to be considered ideal, then we can go ahead and consider it to be ideal. This little pulley here, very low mass. It's made of very low density plastic, and it's very thin, and it's got the grooves cut in it to reduce its mass even more. So we got a very low mass pulley, so it behaves, we say that it's ideal. It's close enough to being ideal that we're good. And also frictionless. Friction forces are a thing. They always oppose motion, so friction forces will be in play in this situation. And you can hear them too, if you listen real quiet. You hear it? Hear it spinning? That means there's friction forces. It's still spinning though. That means really low friction, right? It's still going. Can you hear it?
But I can also see it like slowing down.
Yeah, it's slowing down, yeah. But it's good. It behaves like an ideal pulley. There's no such thing as an ideal pulley, but if you got really low mass, really low friction pulley, then we approximate it as an ideal pulley. Just like there's no such thing as an ideal gas, but you guys approximate gases as ideal all the time when you're doing your gas laws and your ideal gas law. Okay. We will consider all pulleys for this point, for the foreseeable future, to be ideal pulleys. You just got to accept this, right? Accept this for now. Once we learn more physics, once we learn a little bit more about friction forces and about rotational dynamics and rotational statics, then we'll understand why this is the case. For now, just you got to accept it, okay? We're just dealing with ideal pulleys. Anytime we deal with an ideal pulley, it comes with the following implication, and this is what we use, okay? If we have an ideal pulley, the tensions on both sides, and I'm going to put, I can't talk. I'm going to put both sides in quotes for reasons I'll tell you in a second. Tensions on both sides are equal. What do I mean by the tension on both sides? Well, I started today by talking about tension forces and how they act on both objects that they're connected to. If there's tension in the string, it's got to be connected to two different points, and it's got to be exerting the same force on both of those points. One of those points could be where it attaches to a mass or where it's draped over a pulley. In this case, it's draped over a pulley, so I would say that the tension force is pulling the pulley down that way, I can call that F with a subscript capital T. And I know that the same force is pointing up, but acting on the mass that the string is attached to. Just like I had the same tension force acting on me and Brenna, or Brenna and I, when we were pulling the string, we got the same tension forces there. And if we have an ideal pulley, the tensions on both sides of the pulley will be equal, which means the tension force pulling down on the pulley on this side is the same tension force. Okay? Which means that the tension pulling up on M1 is that same tension force. Okay? That's only when we have an ideal pulley. When we learn about rotation in a much greater detail, we'll learn that that's actually not true. But if we got an ideal enough pulley, then we can assume it is true. And as you'll see, hopefully, if I can do my job right, it'll work. Okay? So that's something to understand. If you have an ideal pulley, the tensions on both sides are equal. Okay. All right. With that being said, let's go ahead and analyze this problem. Remember, the question is, knowing M2, you're going to measure M2, measure the angle theta, calculate the value of M1 needed to create a condition of static equilibrium. Meaning, find M1 so that I load up M1, and then I let go of it, and they just sit there. They don't move. Okay. That's what we're looking for. To do that, we have to analyze the forces on both of the objects. When we analyze the forces on the objects, the first thing we do is what? Well, we draw something first. We draw a, what did they call it in the video yesterday? Free body force diagram, free body diagram. Okay, free body diagram. FBD, yeah.
And as I refer to it in my writing.
And I'll tell you guys right now, up until this point, there's a handful of AP students that just fight me on, do it this way and it'll make your life easier. I'm going to tell you how to make your life easier when it comes to analyzing forces and the motions that they cause. And the key is the free body diagram. Okay, a free body diagram is something that's very specific. You're going to have questions, FRQ questions, on the AP exam, on exams in this class, where it will say draw a free body diagram. If you do this, this is FG, that's normal force normal. You lose points there. Those are stupid points to lose because that's an easy question. Forces are vectors, therefore we draw them as arrows. If it's not an arrow, it's not a vector. Okay? I'm not being nitpicky here, this is how physics is done. FG is an arrow. Now that free body diagram makes sense. Okay? You don't label your vectors, it's not a free body diagram. It's not done well, you're not going to get all the credit. Okay? I'm going to show you, Mr. P showed you, I'm going to show you how to draw free body diagrams. I'm going to show you how you can go directly from the free body diagram to the equation that it represents without having to think. Those of you that are bad at free body diagrams because you don't take them seriously, you're going to have a much harder time doing that. Okay? So please follow me here as I go through. We're solving this. We're solving for M1. We're not going to get to the solution until tomorrow, but we're going to solve for M1 here, and then we're actually going to test it. Okay? But I haven't made my measurements yet. Yeah. Right? We're going to make our measurements after we've done the analysis because we're big kids. We don't put numbers in first. It doesn't matter what the numbers are going to be. At the end, I'm going to have an equation. We make those measurements, and then I just plug and check. Right? But I want to analyze this from a theoretical perspective where my results are going to be equations themselves. Okay? I got two objects here within this system. How many free body diagrams do you think I'm going to end up having? At least two. Probably just two. And so I'm going to do M1s first. Why M1? Because it's the easier one. I always start easiest and work my way into the difficult stuff. And I let the math tell me when I need to do so. Right? So I'm trying not to think too much. I know M2's free body diagram is going to be a little funky. So I'm going to hold off on that. I'm going to say I'm just going to draw M1s first. So I draw a dot. Sometimes it's a circle. Sometimes it's a box, depending on who's asking, whether it's the College Board or a textbook. But I'll draw the dot and I'll indicate which mass, in particular, M1, By the way, this is the mass that I'm looking for in this situation. I'm looking to calculate that. Put this down. This is blocking my video. That's a little better. We all know what's going on, right? What we're trying to calculate here. Before I forget. There will not be edits in this video, so I do apologize for anyone that's watching this at home.
Just skip.
I
Plus
do.
5 seconds.
I can have my secretary do it, huh?
Secretary.
Okay. So what for? By the way, when I do free body diagrams, it'll always be force vectors in red. I always do force vectors in red. They're usually in textbooks in red too. Velocity vectors are usually green. Acceleration usually blue. Doesn't have to be, but. So what forces act on M1?
Well, you've got gravity, you've got
One at a time, one at a time. I can only draw one thing at a time.
you've got
I heard
gravity.
gravity.
You've
Now,
got-
before we go on, we draw that vector and then we label it. There's a couple ways we can label the gravitational force, Fg, big F, subscript little g. But we can also label it with what the gravitational force equals.
9.81.
That's gravitational acceleration.
You're right.
To get gravitational force, it's involved with g, but wasn't this in one of the videos? Some said
Yeah, it's from
mg.
Yeah.
Just mass times the acceleration due to gravity. Why is that? I remember when I was told that, first I asked the question, why is the force of gravity equal to mg? Why did they always also call it the weight force? It's the same thing. What is your weight? It is the gravitational force on you. It is a weight. The pound is not a unit of mass. That's why they say you can't convert kilograms to pounds directly, truly, because kilograms is a unit of mass. Weight, force of gravity is a unit of weight. The pound is a unit of weight. It's a force. Okay. That's why they say pounds of force. If they're talking about pressure, sometimes they say foot. Yeah. Anyway. You probably want to get in the habit of labeling your weight forces or your gravitational forces as mg, because that's what goes in the equations. Why is it mg? You'll learn. But we need to know a little bit more about gravity on the large scale before we can understand that. So we will understand. You want to know the weight force on you, you take your mass in kilograms, multiply it by g, 9.8 meters per second squared. That tells you how many newtons of gravitational force are acting on you. Okay? Yeah. So I would get in the habit of just labeling your weight forces as mg. And using weight and gravitational force as interchangeable. They mean the same thing. Okay? Again, we'll talk about how we can theoretically determine g. That's what's going to explain why weight forces are mg. And we can't do that until we learn about Newton's law of universal gravitation. All right, what other force do I have on M1? No normal force here. By the way, flipping physics says force normal, and old school professors, physics professors, say force normal. Most people say the normal force. I don't know why. I honestly don't know why. I say normal force. You want to call it force normal? That's fine. I don't care.
FT.
There you go. Tension force, right?
And that's technically.
Normal forces come from contact with surfaces, okay? If an object isn't in contact with a surface, there's no normal force. M1 is not in contact with the surface, there's no normal force, there is a tension force, right? What can I say about the tension force, the magnitude of the tension force, and the magnitude of the weight force? In my goal here. My goal is to have it static equilibrium, right? They should be equal in magnitude. And so the tension force, now here's another thing. Mr. P from Flipping Physics likes using capital F subscript for the forces. I've gotten the habit of, and most AP teachers get in the habit of, just indicating the forces with the capital letter. Tension force is capital T, normal force is capital N, friction force is big F. We'll talk about that when we start talking about those in more detail though. Yeah. And we know that those should be equal because we know that M1 shouldn't be accelerating if I've done my job right. Right? So those should be the same. Now, from the free body diagram comes the equation. Okay? If it's Newton's first law, then the net force on mass 1, so I'll say net force on mass 1, must equal, actually before that, let's define a coordinate system. Do you think I need to be all weird with my coordinate system here, or can I just use the standard one? I can just use the standard one. Where up's the positive y direction, to the right's the positive x direction, and really we only care about one direction here. What direction is that? The y direction, yeah. So with my free body diagram and considering the coordinate system, I will then say, I will make my statement of either Newton's first law or Newton's second law. In this particular case, will we be dealing with Newton's first law or Newton's second law? Do you cover that in the videos? Newton's law specifically? Newton's first law, an object in motion stays in motion, or an object at rest tends to stay at rest, in the absence of external net forces. So is this Newton's first law? Yeah. It's at rest. We want it to remain at rest. That carries a mathematical implication about the net force. The net force on M1, specifically in the y direction, must be what? Must be 0. That's where my equation comes from. I'll have a set of notes for you, by the way, tomorrow that will have this explicitly laid out, but it's not going to have this specific problem. This specific problem, if you can handle it, you can literally handle any force problem that I can give you. Okay? This is a pretty complex one. Covers a whole lot of different, incorporates a whole lot of different physics when it comes to forces. Okay. How can I go from this to an equation that's actually workable? Well, I like thinking of it this way. And those of you that aren't familiar too much with the summation notation, this just means sum. So if you have this symbol and then things, this just means add up all the things. Right? That's all it means. So this means add up all the forces. Knowing that forces are vectors, so I can put the little vector symbol over the F if I wanted. I typically don't, just to keep the symbols down a little bit, but yeah, that sigma F just means list all the forces. But because they're vectors, if they're positive, make them positive. If they're negative, make them negative. Okay? So I like thinking of that, like kind of unpacking it in the next step, and then listing out all the forces that it represents. If they're positive, make them positive. If they're negative, make them negative. So in this coordinate system, in the y direction, is the tension force positive or negative? It's positive. Is the weight force positive or negative? Negative. It's negative, so I put minus mg. I got a positive tension, a negative mg, and I know those two have to add up to be 0. Well, I can get a nice, neat little equation here by just adding mg to both sides. And when I do that, I see that the tension force is simply the same as the weight force. Notice in words, I already knew this, right? Didn't we already knew that?
Yeah.
I already knew the tension had to be equal to the weight force, otherwise M1 would be doing what? Not just moving, but accelerating, right? Yeah, they could be moving, and we'll see this. If we find where they're in static equilibrium, well, if I give it a little nudge, then it'll start moving, and it'll move at constant velocity, right? Because the net force will still be 0. So it's, yeah, if the net force is 0 on M1, it doesn't mean it's not moving. It means it's not accelerating. Okay? Be careful there with that terminology. Notice how I could bypass this step by looking at my free body diagram. If I know that Newton's first law is at play, meaning the net force is 0 and the system is at rest, I know just by looking at my free body diagram, well, T has to equal mg. So I can go straight to writing the equation from my free body diagram. Okay? The up guys equal the down guys. If we're talking x direction, the right guys equal the left guys. Right? This is how you get it from the statement of Newton's first law. Again, scoring guidelines for AP Physics exams. The student recognizes that Newton's first law is at play in this situation. How can you get that point? By writing net force equals 0. Start by that. That's a point right there. Okay? you leave that out, and you have a bunch of numbers here, you don't get any of those points. You might get the point for the equation at the end, but that might be 1 of 4, 1 of 5. Okay? So don't be lazy here. Don't be lazy. And it just makes it easier. When I do this, after I've done this enough times, okay, free body diagram, straight to the equation. Okay. Sorry, this is specifically M1G, right? Now, can I calculate M1 based on that equation? And the measurements that I'm able to make. Remember, this is a real world thing here. Yeah? Can I use this equation to calculate M1? Do I know the tension? Nope. Can I measure the tension with that? No. All I have is a scale and a protractor. All I can measure is M2 and the angle. So this tells me that I got more work. Yeah. Again, I start in the easiest. These two, I start here because I know it's going to be easier. The free body diagram is going to be less complex. Draw the free body diagram, get the equation. The equation tells me that I got more work to do because I can't solve for M1 because there's no way for me to know the tension without using one of these guys. We're not going to use one of these guys. Force probe, right? I pull on that and it tells me how much force. I'm not going to use that though. So that tells me I got to find another equation. Well, how can I find another equation? Exactly. We just do the same process, but for M2. But as we'll see, our lives get a little more complicated here. And this is the take-home point. The physics of objects on ramps. This is something that some students fall behind on and they just struggle with. So that's why I'm kind of putting it right here kind of at the beginning so that we get some more practice with it. So by the end of this unit, you're perfectly comfortable with this. But yes, I need to draw a free body diagram for M2. And for now, normally I wouldn't do this, but since it's our first time, I'm going to draw the actual ramp, like as a dotted line, right? That's the actual ramp here, showing the direction that the object is going to feel the tension and all that good stuff, okay? Now, what forces are acting? This is going to be M2. So what forces are acting on M2? This is M1G.
Gravity in technically 2 different places.
Gravity in 2 different places?
Wow. Yeah, from your hand.
Yeah, I see what you're saying.
I don't know how to describe it.
I see what you're saying, but there's one gravitational force, and what direction does it point? Straight down, towards the center of the Earth, which typically is straight down. So there's M2G. Okay. What other forces are acting? The normal force or force normal that is perpendicular to the surface. This marker is normal to the surface of this book. It's still normal to the surface of the book. It's still normal to the surface of the book. Perpendicular and away. Always. Okay? So that force is going to go like this. And just like the tension force, you can use whatever notation you want. I've gotten in the habit of just using the capital letter for normal and tension force. Okay. That's not it. Friction. If it's not, we're going to assume 0 friction. We're going to, yeah, I should. And we can assume low friction because for the same reason that's a pretty ideal pulley. That's a pretty ideal wheel. It'll spin for a long time. Loses very little energy to friction. So that's why these things cost like $100. So don't like treat them like they're pieces of junk. Like $100 for that little cart. Just a piece of metal with 4 wheels on it.
You should make it.
It's true. It's like $100.
We should just make one.
So we're gonna neglect friction. What other force? Tension. What way does tension point? Up the ramp, right? So parallel with the ramp. So that would be my tension force. And if we are dealing with an ideal pulley, that tension force acting on M2 is the same as the tension force acting on M1, right? In reality, if this was a pulley that went on a crane, that had steel cable draped over it, that was lifting up I-beams that weighed tons apiece, that pulley is going to be nowhere near massless. That pulley is going to be heavy enough to where you won't be able to lift it. And it's going to have a whole lot of friction in it. Okay? That friction is going to heat that pulley up when it's lifting those I-beams. Okay? That is much more complex. We don't get to that until we can deal with ideal pulleys. Okay? Once we can do ideal pulleys and we start learning about rotation, then we can move into real pulleys. Okay? So, yes, this isn't in reality, but we do deal with this stuff in reality, specifically when you're building skyscrapers. You've seen those cranes, right, that go on the top of skyscrapers? That's how skyscrapers get built. They used to trip me out as a kid thinking about how they build skyscrapers. No, they build them, they put the crane on top of it. And as the building gets bigger, they just move the crane up, right? And that crane has steel cables that go all the way to the ground and lift those beams all the way up to where they need to go, right? And those pulleys are not ideal pulleys, but you can't deal with those pulleys unless you can deal first with ideal pulleys. Yes, sir?
Is the normal force always equivalent to the gravitational force?
Nope. That's a good question. The question is the normal force always equivalent to the gravitational force? It will be if the object is sitting on a horizontal surface. Okay? The normal force will be the same as the gravitational force. What if the weight force becomes too much? Let's say I put a weight that's on top of this table that's too much, and the table isn't sufficient strength to provide the normal force necessary to keep the weight. Then it crashes through and it breaks the thing, right? Yeah.
Anytime there's a ground, you sit on a lawn chair.
Don't you mean your mother?
That hurts my feelings. Hey, I just spent several days eating barely anything. I've lost I think I've lost more than 5 pounds. And I don't have those pounds to lose.
You don't have enough normal force.
Okay.
The chair doesn't have
No idea.
Yeah, if you sit in a lawn chair, Isaac, and you break that lawn chair, that means that lawn chair was not capable of providing the normal force on you needed to counteract the gravitational force, your weight force.
Okay. I can buy you a titanium lawn chair.
Okay.
Collapse something.
Now, what was our second step over here? Free body diagram, then coordinate system. Would our standard coordinate system be... Now, okay, there's a little thing called relativity. You might have heard of it.
Yeah,
I actually have it. My parents bought me this for Christmas whenever. Back when Christmas was fun and I got to get stuff for Christmas. Now it's just very expensive. This is Einstein's 1912 manuscript on the special theory of relativity. His first paper on it was in 2005. Took him 7 or so years to develop it into this. If you want to see what actual theoretical physics done by Einstein looks like, it's right here. Guess what? Einstein shows all his work. Not only does he show his work, he explains all his work. This is physics right here. This is handwritten by Einstein in the early 1900s. One of the main postulates of relativity is that all observations and calculations are equally valid, even if you're using different coordinate systems. Okay? So I could be watching this situation play out and use a totally different coordinate system than Mena, but if we calculate the acceleration of this system, as long as we do our work right, we get the same result, okay, regardless of the coordinate system. What that tells us is that coordinate systems are arbitrary. You can pick whatever coordinate system you want. We can use different coordinate systems, but our results, our predictions will be the same, as long as we don't mess up with our work. So, that being said, you can choose a coordinate system, and if you're like me, you want to choose a coordinate system that reduces the amount of work that you have to do, right? So there is a most convenient coordinate system that I can impose here on M2 that will be easier, meaning less work for me to do. How can I do that? How can I define a coordinate system that will make this the easiest? That we're... But shift, dude?
Yeah, like that.
Yeah, like this, right? Or like that.
Well, yeah. So
We're orienting it so that one axis is parallel to the ramp, and one is perpendicular to the ramp. Why do we decompose vectors, guys? To get their components to align with our coordinate axes. Is the bell about to ring? Oh my gosh. So we're going to use this coordinate system. And that's fine. Why do we use that coordinate system? Because the tension force is now in the negative x direction. So we don't need to worry about it. It's in the x direction. We don't need to decompose it. The normal force is in the positive y direction. We don't need to decompose it. All we have to decompose is m2g. And we'll start there tomorrow. But what if we used our standard coordinate system, what vectors would we have to decompose? Not all of them.
Oh, two of them.
The tension and the normal force.
Oh, yeah.
And it gets really gross if you have to do multiple vector decompositions on a single free body diagram. Okay. All right. We'll pick it up from there tomorrow. Hopefully this video worked.